anyhow. I would like to make you a presentation about a project we had since a few years about caustic exploration. I tried to translate that, it was funny, but I'm not sure what the translation you will say after the pitch. And this should be my name. So then Pierre will have to correct me, but I think it's okay. Thank you. After the speech of Francesco, I will just start by the end. Sorry, so I have to reorganize everything because I think this is quite interesting. Okay, here it is. Yes, from my experience, what should be a good project? A good project has to carry 4 ingredients of success. The first one is obviously to pave new research avenues, and it's a term of our time, to go into a transdisciplinary process in order to go out of your own comfort zone, and you will find here a new view of your own scientific issue that is very interesting. The second point is impact territory. Normally when you are making a project, you always want to sail the moon, to reshape the moon, to go on Mars. But you will see, to my opinion, that this will start in your own garden. And you will see the project I will present to you is about water, it's about water resources. But this question of water resources is a worldwide issue. But think about the question of resources in your own town, in your own house. The third point is how to network people of goodwill. All this is not so easy. So if you find some good people, please keep them close to you to make some good projects. And the fourth point, if you have the third one, the 3 firsts, should be just a technical issue. And I agree with you that we have to lobby our institutions such that this point in which we are not really competent should be a technical issue. This is just on paper, okay? But we have to lobby our institutions so that this is not a question. And then we should focus on the third one, on the 3 one. Okay, this is just an introduction, and now let's dive into the guts of this presentation. I will not talk about ocean in this presentation. I will talk about inland water. We will go here underground, okay? Not underwater, but you will see that there is a lot of things that are comparable. So, this is the outline of my presentation. I will just start by a global presentation of what is karst. Karst is an underground landscape that is formed by the dissolution of limestones, dolomite, gypsum, or marble, okay, that creates this hole underground. And this hole can be filled with water. And this water can be exploited. You can use this water. And in fact, we are using this water. But the knowledge we have of this karstic network is so limited that we are not really knowing what's happening down there. So, the creation of karst is related to the 3 chemical equation. Okay, when CO2 is with water, you have carbonic acid that in different period of time creates a proton and bicarbonate. And when this bicarbonate meets ions of calcium, this is creating calcite. This is the other way when you are creating calcite and you are depositing this calcite into this crazy landscape underground. We have some surface stigmata of what is karst. Here you have some example in China, in Madagascar, on the previous slide, and here in Lebanon we have this crazy landscape, okay, naturally formed by the dissolution of karst. But as we are going underground, all the chemical processes are acting there. You have these incredible forms, you have these giant crystals. In Mexico there are other caves like this, and you have these calcite deposits that are forming this incredible shape. But the most important thing of this karstic environment is that it represents a huge groundwater reservoir. And in order to use this underground water, we need to know more about this environment. But knowing more about this environment requires, oh, this is not working. Okay, requires to navigate in this, I don't know. I'll try this way. Okay, this is not working. Anyway, it's not fundamental. Yes, we try to navigate in this very confined environment. Okay? Cave divers are doing that, but cave divers are crazy people. Okay? So if you want, just an advice, if you want to come with me to play, to come with us to play in this environment, and you have to choose cave divers to come with you on terrain, please select the oldest one. Okay? This is very, very dangerous, but this is also very, very exciting to go on terrain with such professionals. Okay? Okay, this is another example of a karstic environment. This is the largest karstic reducers in Europe, called Fontaine de Vaucluse. And this is quite interesting because this has a huge seasonal variation. Okay, it can be very dry, or it can discharge all this water in the valley. And this is known, so there is no city in this valley. Okay, this is all preserved, which is not the case everywhere, as we will see later. 50% of the drinking water in France is coming from karstic region. Okay, but this is not the only country where this percentage is done. And there is a very specific situation that occurs around Montpellier, where I come from, is that for geological reasons I will show you after, there are some very deep karsts in this region. And our hydrogeologist friend have done the Médicis Observatory of karst, where they have spread out in this catchment basin between these two rivers, the Vidol and the Hérault, which is the catchment basin of Montpellier. They have spread out 400 points of measurements in order to have an online state, okay, of this karstic network here, to know the status of the refillment of this karst due to heavy rainfall that we have. But this is just static measurements. Okay? In order to complete the knowledge of this network, we need to have more precise and punctual measurements, in situ measurements, inside the karst itself. And this is what this project is about. This is another view of the problematic of Montpellier, but I think that this is also emblematic of what's happening in karstic region. So I will explain. Originally, during Romanian times, people were catching water directly in the spring pools, in the spring pool. Then, because of the growth of the city, we have to find a way to have more water and to guarantee the quality of this water. Then they explored all this conduit, 5 meters upstream, and they decided to build this underground pumping plant called the Avia station, just to catch the water directly in the karstic network. Okay? This is the situation, but the population is still growing, and the water demand is also increasing. Then we need to find a way to have more access to this underground water. During summer, we are taking water elsewhere, even if this spring is giving water. But when they were exploring this conduit, a diver that disobeyed to the mission plan went upstream and discovered a huge potential reservoir here, in which pumping directly should be a very good idea in order to decrease the seasonal variation of the spring. But the problem is, all this network, all this spring is linked, and we know that, with deeper network that goes directly to the sea. And we know that we have located some underwater marine exurgences there that are linked to this network here. And the consequence would be, if we increase the pumping here, then we shore. So it's a huge hydro system, okay? It's an hydraulic problem that we have to capture and we have to model in order to have an active management of the underground resource. It's also a marine question because these springs that you have in the water are everywhere around the world. And it could be a very nice idea to capture this water directly at the sea. This water will be less salty than the sea water, but it will be salty. So not directly exploitable for drinkable resources. But for industry it can be used. And there are some projects, and this project was called Meditate project, about the location and the qualification of this water directly at the sea. And you see, if you have an AUV and you put just a simple CTD on it and just an echo sounder, you can have the bathymetry here, the temperature map, and the conductivity, and you see that you can locate the spring directly at sea. But this is not a story. Here, the project is about exploring the underground continuation on this. Another aspect, I won't have any videos, I'm sorry, I don't know why. Oh, this is a beauty. Okay. Another aspect of the question is the hydrogeologic risk. Because these karstic regions, okay, are acting like a sponge when it is raining, and it is the case in our region because we have a special geographical situation that makes all the storm staying statically here, and it is raining for days, and suddenly this karst is filled with water, and because of violent transfer of charges, this water suddenly appears in region, in fragile and sensitive region, such as the center of towns. Here is a flood we had in 2005, and here is the center of Montpellier. Okay, here normally you have a very little and nice river that is flowing there. And suddenly this river goes a huge river, okay? A torrential river. You know the problem, this happens everywhere around the world. Another consequence is the appearance of these skin holes. When you are flowing, when this water is flowing on the ground, it catches all the ground there and suddenly everything collapses. In the region, in the sensitive region, where it is not expected, of course. Another consequence is near the Dead Sea shore in Israel. The Dead Sea is decreased, the level of the Dead Sea is decreasing. And you have some caves that were filled with water, very salty water. And now these caves are empty and everything collapsed. And you have houses that disappear in these holes. Okay, this is dramatic. It's a very dramatic situation. So the stakes for this karstic exploration is the prospection, the preservation, and the management of the water resource, for sure. And another very important point is how do you spread these pumping stations all around the Kherson Basin, okay, in order to close the loop on the state of this hydro system. Another very important thing is how do you make the drill, how do you access to this resource? We had a situation near Montpellier where they drilled for 200 meters and they missed the vein. Okay, they were a few meters away from the vein. Okay, it's $100,000 or euros that just vanished because of this. If you are able to put there a magnetic loop that are guiding the drilling head such that you can guarantee that you will access to the vein, then it will be of huge interest. The other consequence is in this karstic network, when you have, imagine you have a pollution somewhere. You have a truck charged with a chemical thing that just goes down in the river. How does this pollution affect your pumping strategy? Okay, the supply of the city. And almost how much time do you have to switch to another pumping? Okay, this has to be known. Okay. The hydrological risk assessment, okay, forecasting and make decisions, help institutions to make decisions about this. Pinhole detections, of course, And there was also another proposition made by our partners in Montpellier, is to spread cleverly this pumping around the catchment basin, such that in case of a heavy rainfall, you favorize certain pumping to empty certain parts of the course, such that when the rain is coming, okay, the course is acting as a flow down control. Okay, you are stocking this water instead of letting it flowing in sensitive region. Why this problem is generalized around the Mediterranean basin? Okay, it's that during the Messinian event, okay, you have a closure of the Gibraltar Strait, and the desiccation of the Mediterranean Sea occurred, and the level was 1,500 meters lower than the actual level. And the karstification process, okay, the karstogenesis, went very deep. And people now are thinking that this karstic network can be encountered at up to 2,000 meters depth, okay? And this sponge, okay, is filled with water that we can eventually use. We had some friends, some divers, that went in a dive near Toulon, and they went in the cave. They were 100 meters above the sea level, and the water was still fresh, sweet. Sorry, the water was still sweet. It was unexpected, and they were very nearby by the sea. And then, okay, the water came back, and this is the reason why this question is global for the Mediterranean scale. But it's also true. It's also true at the global and the worldwide level. Okay, this is the karstic map of China. Okay, this is the karstic map of Malaysia, of Vietnam. This is the karstic map of Croatia, Spain, and Portugal. Okay, we have to manage these groundwater resources. It's a huge, interesting question. How do we do this? First, the goal is to have a clear cartography, as clear cartography as possible of this network, to make seasonal measurement with reproducible protocols. Eventually, to put sensors in this network. Okay. In order to obtain a geomorphology of the flooded zone, to have indications of volumes and seasonal variation, of course. But in order to do this, we will see our first experiments, but I'm afraid I cannot show you the video, but we will see. Show that we need to develop new sensors, new acoustic sensors in these confined environments. But it is very challenging. How to develop new models, how to have uncertainty, a clear evaluation of the uncertainty of our own models, and to have an ND geomorphological models. It's not enough to have the 3D modeling of the cave. You know, to have indication of temperature, of salinity, of magnetic artifacts. Okay, it's an ND modeling questions. And the global issue, the global objective, is to have acquired knowledge about the karstic dynamics. Just a rapid overview of what happens at the beginning. In 1967, the Commandant Cousteau, with Deleuze, the founder of the COMEX, okay, made a very interesting, it was the first dive with a robot. It was operated in the Fontaine de Vaucluse, and the first attempt they reached 106 meters depth. They reached this zone in 1967. And then they developed another robot called the Sorgonaut, and they reached this depth of 243 meters. Then, problem occurred. They developed the second thing, and they were stopped because of the cable length, so they made another one, and they lost it at 233 meters, because it was stuck in the remaining lifeline of the diver. Okay. So they developed another one, the Sorgonaut 3, in order to recover the system. Sorgonaut 3 were lost at 150 meters. So we have two robots here that are completely blocking the entrance of the chasm. So, what they did, they developed the Sorgonaut 4 to recover the two first machines that was lost in 1983. Then we had 3 machines like this that were lost because of the cable. Because of the cable. Then they asked the divers to clear the chasm, of course. And this underlines the interesting question of what about risk-taking for divers to save the robots? Okay. Then the story continued, and they touched down at 315 meters with the Modexa in 85 and the Spellinot in 89. Then they developed a new machine with the new sensor suite in order to have a more precise map of the chasm. And the Spellinot 3 was lost at 164 meters. Then they developed a new system provided by Comex in order to recover this one that was lost at 164 meters because of the cable. Okay. Okay, this is a robotic failure. But this is a huge, interesting teaching about how do we put these robotic machines inside this very highly confined environment. And okay, the chance was cleared by divers. Same story happened all around the world. Here is an example of Italy. And this is developed by people in California, by Billstone Aerospace, that developed this crazy machine that is the X system. It's an AUV, completely autonomous, with 46 echo-sounders, and the system is able to sample itself, but in C-notes that are this incredible geologic artifact, completely, these are flooded skin orbs, basically, okay? And I don't want to criticize the machine, it's a very piece of technology, but the exploration is more easy because it's just vertical. Okay. This is another example of colleagues that are going there. They developed Unix mine system to explore flooded mines in order to see if it would be interesting to reopen this mine exploitation. Okay. And here is the project we are proposing. In this configuration, okay, this is an artist's view of what we would like to do. This is on the paper. I will show you where we are. So the idea is, in this confined environment, when you are discovering the environment, the expert has to be in the loop. The robot itself cannot decide if you have a location, if this way is better than this one. Okay. We are not developing expert system as we did decades ago. Okay. So the idea here is to have a system with a sensor suite that will allow the system to be centered autonomously in the cars. Okay. And the system has a clever mechanical device to lay down the cable as it is progressing in the conduit. Okay? As it is progressing in the conduit, it is cartographing the environment, and when you are at the end of the mission, then the idea is to cut the cable and to go back autonomously, navigating in the model you have built on the way in. Okay, this is the idea. We are also working on the development of new sensors, the principle of the acoustic scheme. Okay, how can the robot can feel its environment all around here, okay, around it, and the principle of an active cable, because if you cut the cable and the cable remains in place, this is the lifeline of the system. Okay, so the system has to locate itself with respect to this lifeline. These are the challenges that are related to these questions. So there are a number of them. So please pick a couple of them and come and play with us. Okay. We have the sensor development part, the navigation problem, and the very specific SLAM question. With this question, the vacancy evidence grid, when you are in the cast and you are surrounded by these rocks, and where to go? Okay. How can you find the navigable space? Okay, choose your direction. The guidance problem. How do you include? This is quite different than we use to imagine robots. Here, okay, generally you have the robot that is carrying sensors for its arm navigation, and you have mission sensors that are requiring information in the environment and to give this information to experts that are using them. In this situation, you need to use this information in order to build model within the control loop. So this model made by acoustic sensors is heavy, very huge model. Okay, you need to play with the size of this model in order to use them in the control loop. This is a very interesting question. Robustness, open loop stability. Okay, I have to accelerate that thing. We have the robustness question. In this environment, the buoyancy is not guaranteed because you can have faulty intrusion. Okay, when you are laying down the cable, your arm mass is changing, so there is a global robustness question. The current is varying. Okay, for the same debit, if the section is reducing, then the current increases. Okay. The software architecture question, the dependability, and what we are calling the guarantees of performance is when you are sending a robot inside the source of delays, it's a site that is in exploitation. You have pumps there. You cannot risk to lose the robot so that it will be brought into the pumps. Okay. This will increase drastically the budget of the mission. Okay. I'm not talking about insurance. Then the question of how can we guarantee that, not even if the mission is not achieved, that you can guarantee that you will recover your system. Okay, you will not pollute this environment, etc. and other questions. So we developed this system, the ULIS system, 12 thrusters, because of redundancy in actuation, and associated with a two-layer system architecture. We developed here the ULIS, and we developed also the nav scoot where we took all the sensors of the system and we put them on a scooter driven by a diver. We made two first experiments in the chasm of Wuhan CMPRS. This was the original knowledge we had on the chasm, okay, made by divers, okay, with decal meters and compass, okay, just that, just that. And here, normally the video was beautiful. You have to believe me, okay. Okay, I will try to show. And then, okay, then we have a profiling sonar in order to acquire the 3D geometry of the system. But the problem we have is this profiling sonar, okay, that is sampling the environment all around the robot, okay, has a very low frequency. It requires 6 seconds 6 seconds to make a complete turn. How can you close the loop of the system on such a low sensor? So we mount a DVR on it such that we can complement, we can predict what the information should be between two measurements. Okay? But in this confined environment, we chose the bad DVR, and we lost 80% of the measurements of the DVR. So there is a real question about what acoustic device we should use there. Anyway, you have here 300 meters of the cartography of the entrance of the chasm of Wuhan CMPRS. And we are also working with guys from mathematics in order to compute volumes and to compute the uncertainty map in the volumes of the... And here is a virtual visit, very static, I'm sorry, of the chasm. I will try to play the video after. And more recently we made another experimentation because in these conditions you cannot guarantee that the water will remain clear. Then you need to rely on acoustic sensors. But in the first attempt, the water was very, very clear. So what about using vision in this situation? So we took the nav scoot and we took a stereo system here, and we gave the nav scoot to divers, and they were visiting the Turban River, another caustic network with this. And okay, sorry for the video. And we were using this. We chose this site because it has some particularity, this four chimney, and we wanted to know how here we have four samples, okay? Just measuring across the environment and how the echosounders can measure these cheminées, okay? And we confirm that the static was okay. Okay, finished. And this is the photogrammetric reconstruction of the chasm, okay? And this should move. Okay, it's not moving. I'm sorry. This is a question of developing new sensors. In the near future, we have a project to explore this unknown zone upstream to the dumping station. This is a different project we are proposing, and we are addressing this quite interesting question of what's the business. The business is huge. The business is huge, but it has to be organized because the market is not existing because we don't have the tools, and we are proposing to develop them. And then we are open to international collaboration on this subject. Okay, thank you very much.
Thank you. So we are running out of time. We want 2 questions.
Thank you, Lionel. Very nice. Very nice. So we talked yesterday, and I think you were in favor of not going for a survey of those spots at sea, where the city water.
Yes.
Having seen your presentation, I'm more and more convinced that we should include that, because this would give people a broader vision of the network that is now in use. I think it makes it even more glamorous. So something to discuss.
Yes, for sure. It's part of the problem. Okay, I will just show you this. It's part of the problem, for sure. It's a natural continuation of the classic network that is at sea. Okay, I think that the consortium we built is just too small to address all the questions.
Yeah.
But it has to be addressed. And for this, I think we are really open to international collaboration in order to address all the questions. Of course, this is natural continuation of the process.
But I think it would be nice to demonstrate that one can work at the same time inside the cave and then see somehow come these together.
And I think that there is a huge interest for hydrogeologists to have simultaneous measurement in land and in water.
Right.
Yes.
Okay, thank you again. I think we have moved to this. Thank you very much. Thank you, Lena.